Proteins are basically the tiny machines that run our bodies, but they're so incredibly complex that just looking at them, well, it's almost impossible to understand what's going on. So how do we get around that? In this explainer, we're going to break down a really powerful technique that lets us turn these messy, tangled structures into clean, simple networks that we can actually analyze.
Okay, so here's our game plan. First, we'll kick things off by looking at why we even need a model in the first place. Then, we'll dive right into the network solution, and I'll show you how to build one yourself, step by step. After that, we'll get to the really cool part, a surprising discovery these models have shown us. And of course, we'll wrap it all up with a quick and dirty summary and some tips so you're totally ready for any exam questions on this topic.
All right, so first things first. Why can't we just, look at a protein and figure it out? The short answer, they are just mind-bogglingly complex. I mean, just take a look at the ribosome here. This isn't some simple little chain of molecules. It is a huge, tangled up, three-dimensional machine with thousands of different parts all working in perfect harmony. Trying to understand it all at once, that's like trying to map out an entire city by staring at a single brick. You'd just be completely lost in the details.
And that really brings us to the core question that drives this entire field of study. We have to find a way to zoom out, to see the bigger picture, the patterns, the connections, without getting hopelessly bogged down in all the atomic details. We need a model. And this is the solution. This is the magic trick. We're going to learn exactly how to take that complicated, messy ribbon structure you see on the left and transform it into the clean, simple, and super easy to analyze network on the right. What we're doing is trading some of that fine-grained detail for a clear, understandable map of how everything is connected. And for our analysis, that's way more useful.
Okay, so how do we actually build this network? Well, the kind of network we're talking about has a specific name, and this is a big one you'll want to remember. Residue interaction graphs, or RIGs for short.
The best way to think about a rig? It's literally a social network, but for a protein. Seriously, we stop worrying about every single atom. Instead, we focus on the main players, the amino acid residues. In our network, each residue becomes a person, or a node. And if two of those residues are interacting, we just draw a line between them, an edge. That's their friendship.
And this slide just lays it all out, doesn't it? The analogy holds up so well. An amino acid residue, that's a person, our node. A physical interaction between two of them, that's a friendship, our edge. A little group of residues all clustered together, well, that's just a clique of friends. And the way information travels through the protein, that's exactly like degrees of separation between people. It's a fantastic way to think about it.
Okay, so we know what a rig is. Now for the fun part. How do we actually build one from scratch? This is the step-by-step guide, so you're going to want to pay close attention here, because these are the details that pop up on exams.
It really just boils down to 4 main steps. First, we have to identify our nodes, which, remember, are the amino acid residues. Simple enough. Second, we have to figure out how we're going to measure the distance between them. Third, we set a cutoff, a threshold, that defines what actually counts as an interaction. And finally, step 4, we draw the lines, the edges, between any nodes that meet our rule.
So that second step, defining distance, is super important. As you can see, there are a few ways to do it. But honestly, the one you'll see most often, and definitely the one to know for an exam, is measuring the simple straight-line distance between the C-alpha atoms of each residue. It's reliable, it's straightforward, and it gives us a great picture of how close two residues really are.
So where does all this data even come from? It comes from something called the Protein Data Bank, or PDB. Think of it as this massive public library of protein structures. And if you peek inside a PDB file, you'll find exactly what we need. These precise X, Y, and Z coordinates for every single atom in the protein. This is our raw material.
All right, now this formula, this is the one you absolutely have to burn into your memory. It's just the standard Euclidean distance formula you probably learned in math class. To get the distance, which we call Rij, between any two residues I and J, you just plug in their coordinates. You take the difference between their X's and square it, do the same for their Y's and Z's, add it all up, and then take the square root of the whole thing. Okay, so once we've calculated that distance, Rij, we need a rule. A simple yes or no rule to decide if we draw a line. That's where the adjacency matrix, Aij, comes in. Think of it as our rule book. We pick a cutoff distance, RC. If the actual distance between our two residues is less than that cutoff, they interact. So Aij is 1, and we draw an edge. If the distance is bigger, Aij is 0, no interaction, no edge. It's that simple.
All right, so we've gone through all the steps, we've built our network. Now for the big question. So what?
What does this model actually tell us? And believe me, this is where it gets really, really cool.
To really get why protein networks are so special, let's look at the two extremes. Over on the left, you've got a regular network. It's super orderly, everyone is just connected to their immediate neighbors, it's very predictable. Now look at the random network on the right. It's pure chaos, connections are all over the place. But that chaos means you can get from any one point to another in just a few hops.
Okay, now look at the protein network sitting right there in the middle. What do you see? It's not perfectly neat and tidy like the regular one, but it's not a total free-for-all like the random one either. It's kind of a mix of both, isn't it? It has those local, neighborly connections, but also some of those long-range shortcuts. It's a hybrid.
And this special in-between property, this best of both worlds situation, has a name. It's called a small world network. It has that high local clustering, all those little cliques, of a regular network, but it also has the short average path lengths of a random network. It's exactly the 6 degrees of separation idea you've probably heard about in social circles.
And look, this isn't just a cool idea. The data backs it up completely. This chart is from a study of almost 1,000 proteins. The vertical axis, L, is basically how many hops it takes to get from one point to another. The horizontal axis, C, is how clicky the network is. Random networks are down here, low path length, low clustering. Regular networks are up here, high path length, high clustering. And where do the proteins land? Bam! Right in that sweet spot. High clustering, but short paths. Classic small world.
Whew, okay, that was a lot, I know. So let's lock it all in. We're going to do a super quick summary, and I'll give you some tips to make sure you absolutely nail this stuff if it comes up on an exam.
All right, rapid fire review. What are the must-knows? A rig is our model. Nodes are residues, edges are interactions. We calculate the distance, Rij, using that Euclidean formula. We use the adjacency matrix, Aij, and a cutoff Rc to decide if an edge exists. It's either a 1 or a 0. And what we find is that proteins are small world networks, which means high clustering and low path length, the best of both worlds.
And listen, here are a few common traps people fall into on exams. Let's make sure you're not one of them. First, pay attention to which atom you're using for distance. Usually C alpha, but double check. Second, please don't forget to square the differences in the distance formula. It's a super common mistake. Third, the adjacency matrix is just a 1 or 0, yes or no. Don't overcomplicate it. And finally, if you have to define small world, you must mention both high clustering and short path length to get full marks.
Okay, and I want to leave you with one final question to chew on. We've just established that this small world architecture seems fundamental to how proteins work. So, what do you think happens if a genetic mutation comes along and knocks out a key player, one of those super connected hub nodes in the network? How could that one tiny change ripple through the entire structure and totally disrupt its function? Something to think about.